Hello, I'm Dave Hewitt, and today I'd like to tell you about some of the work we've been doing at Sheffield on Grand Challenge 1.2, which is concerned with manufacturing of features for in-service monitoring. So first, I'd like to give you a bit of an overview into what Grand Challenge 1.2 consists of. Essentially, the focus of the challenge is to utilise fibre brag gratings to monitor parameters within electric machines for diagnostic and prognostic purposes. So the key parameters which an FPG can monitor are strain and temperature. It's also possible to monitor other parameters, for example vibration, by packaging the sensors in a manner such that the stimulus of interest is transferred to the sensor in a way that can be detected. So now I'd like to give a brief summary of what I'm going to cover in this presentation. So first off, I'm going to give a brief introduction into FPG sensors and how they operate and how we use them. Then I'll move on to some initial testing results which we've got from those sensors. After this, I'll then move on to discuss the modelling of strain, decoupling methods which can be used with the FPG. Then FEA modelling of a machine slot will be shown. And finally, we'll move on to a little bit of machine lifetime prediction. Okay, so now I'd like to give a bit of a brief overview into what an FPG is and how it works. So essentially an FPG sensor is a sensor which is integrated into an optical fibre, and it consists of a series of gratings which are etched into the fibre at a prescribed separation. This grating causes light that's shone down the fibre to be of a certain frequency to be reflected back. And by detecting this reflected light, it's possible to infer what the spacing of the grating is. By applying an external stimulus to this sensor, for example a strain or a temperature, the spacing of this grating will change, and as a result the frequency of the light which is reflected will also change. By detecting this change in frequency, it's possible to infer the magnitude of the stimulus which was applied to the FPG. Because FPGs only interact with light of a certain frequency or light in a certain frequency band, it's possible to put a number of them in an array on the same fibre, as long as they're all set to work at different grating spaces and therefore different light frequencies. Doing so allows you to have one single fibre with multiple sensors, which can potentially simplify the cabling process when producing the machine. Okay, so this slide shows an example testing a two-element FPG array. You can tell that it's a two-element array by looking at the frequency spectra that's obtained from it. You can see in that spectra quite clearly that there are two very distinct peaks, one relating to each of the two FPG elements within the array. What we've then did was applied a temperature stimulus to both of these sensors and recorded the resultant transient response. You can see on the figure on the right the inferred temperatures which were obtained from this test. So in order to use an FPG as a temperature sensor, there are a few things that need to be taken into consideration. The most important of which is that because an FPG is sensitive to both strain and temperature, both stimuluses will cause a shift in the measured wavelength. So in order to accurately measure a temperature, it's necessary to isolate the FPG from the external strain which could be applied to it. This can be achieved by placing the sensor inside a rigid sleeve, and potential materials for this could include steel, copper or PEEK. Because the application we're looking at ultimately is in and around machine windings, it's desirable to use a sleeve which is an insulator rather than a conductor. So as a result of this, we believe PEEK is probably most suitable for our particular application. This slide shows some modelling which was done to determine how much the transient response of the FPG would be affected by using different sized PEEK sleeves. You can see from this slide there were two different models considered, which can be thought of as the best and worst cases in terms of positioning of the FPG within the sleeve. The one which I've referred to as the mid model on the left, basically with the FPG perfectly centred in the tube with a cushion of air all around it, whereas the edge one is the case where the FPG is resting on the edge of the tube. in reality, the reality is likely to be somewhere between the two, more than likely. As you can see from here, basically, the larger the tube which is used, the slower the transient response. That can be attributed to the fact that obviously the larger tube has a larger thermal mass, so there's more of it to heat up. What you can see is regardless of which tube is selected, the transient response is still under about 5 seconds, which in terms of when you consider the thermal mass of an electric machine, that should be adequate. The other thing to notice is when you look at the smaller tubes, that can be dropped down to 3 seconds at the most. So to perform some testing on these temperature sensors, we produced a motorette, as you can see in this slide. The specifications of it basically conform to the IEEE 117 standard for the core. The winding is an 80 turn 0.8mm wire winding, and a 0.8mm outer diameter peak tube was used to protect the temperature sensor from the external strain. This was inserted into the middle of the coil by stopping winding halfway through and placing the tube and then completing the winding. We also, for reference, attached a couple of thermocouples which were located at relatively close positions to where the FPG sensors were in the assembly, which gives us something to compare the temperature measurements to. To actually test the sensors, we heated up the coil by applying a DC current to it, a constant DC current, and logged the temperature during the test. This slide here shows the results of that testing, and what you can see, the dotted lines represent the thermocouples and the solid lines represent the FPGs. You can see there's not a great deal of difference between the sensors, and the transient response time is very comparable between them. There are some slight differences between the sensors, but that can primarily be attributed to the slight difference in placement within the winding. So in addition to the temperature in the windings, another parameter that's of interest is the stress that's on the insulation layers of the winding. To study this, we've built the FE model, which can be shown in this slide. It uses 1/8 symmetry, and the wires are 0.8mm in diameter. The coating layer on the conductors is 0.025mm. To apply a thermal stress to the model, we apply a fixed temperature to all the elements within it. And the coating that we're interested in is the one which is in the middle of the bundle, which is highlighted in the bottom left of the model. So this slide shows some sample results obtained from that model. In this case, the spacing between the conductors was 0.05mm. A 180-degree temperature was applied, and this shows the strain values which were obtained. So you can see when you consider the conductor, the radial stress peaks in line with the other conductors in the model, which is the opposite of the hoop stress, which peaks in the gaps between the conductors. You can also see that the axial stress is relatively consistent across the length. So you can see from this slide the resulting von Mises stress across the coating layer. You can see that the peak value occurs in line with the adjacent conductors, and you can also see that along the axial length of the sample, the stress is relatively constant. So one of the parameters which is interesting to consider is the impact of conductor spacing on the coating stress. To do this, we produced a range of models with a variety of spaces from 0 to 0.3mm. The results of these at different temperatures can be seen on the graph on the right. We also calculated a lower limit for each temperature, which is denoted by the dotted line. This was calculated by only having a single conductor in the model with no adjacent conductors, and is the equivalent of the conductor in a very large amount of epoxy with no other conductors. What you can see from this is that conductor spacing can have a significant impact on the level of stress which is experienced by the coating layer and can't be ignored. So another parameter which is of interest is the boundary condition of the model. So all the results we've been shown up till now assume that the the winding can expand in an unlimited manner, and as a result, the outside surfaces are free to move. This is not an accurate representation of what will happen within a winding, within a machine slot, as there will be some constriction applied by the slot. An alternative model has been produced whereby a layer of steel is applied to the outside of the model, which emulates the presence of the iron slot. The resultant stresses from this can be seen on the slide in the right. What you can see comparing that to the free to move on the left is that in each case the stress is quite a bit higher when the constriction is applied. So in order to validate which of these models is more representative of a winding within a slot, it's necessary to model ideally a full slot. In order to do this, what we need to do is simplify the geometry, as in order to model a large number of conductors with the coating layer in sufficiently high resolution would require a very large number of elements, which would cause computational issues. As a result of this, what we wanted to see was, is it possible to omit the coating layer on conductors which are not the conductor which we're actually directly interested in. To try this, we used the model which is shown here, whereby we replace the coating layer with one of the surrounding materials, so in this case the epoxy, but we also tried replacing it with the copper to see how that affected the resultant stress on the conductor of interest. So you can see the results on this slide. You can see that changing the coating layer for epoxy has very little impact on the resultant stress in the other conductors. However, using copper gives less ideal results. As a result, it's preferable to replace the material with the epoxy, as they are relatively similar materials. This is helpful when we come to model the entire slot, as it means we don't have to put the very thin conductor coating layer on every conductor. We only have to apply it to the conductors where we're directly interested in measuring the stress, which simplifies the model. So this now shows the model which we were using to represent the slot. You can see here it's a half slot model. Here the conductors are spaced by 0.05 millimeters, and the diameter of the conductors is 0.8 millimeters, as was the case in the previous models. The coating also remains unchanged at 0.025 millimeters. This model initially is used to identify the position of the conductors of interest and also where the hotspot is likely to be within the winding. After we've done that, we will then apply a coating layer to the conductor of interest to see how the stress is. So the first use of this model is to determine the location of the hotspots within the winding. To achieve this, we used an electrothermal simulation whereby 5 amps was applied to each of the conductors, which equates to a current density of 9.95 amps per millimeter squared. The machine outer surface was also constrained to 150 degrees to model the cooling of the machine. You can see from this slide the location of the hotspot, which is in the middle of the winding bundle, which makes this the conductor we're most interested in determining the stress of. So based on this conclusion, we've added the conductor coating layer to that conductor, as can be seen. The position of it is located by the asterisk. We then perform mechanical simulation, but in mechanical simulation we assume a uniform model temperature. This was done to allow direct comparison between the hexagonal models and this one. So this then shows the stress in that coating that I've just highlighted. We performed simulation at a range of temperatures from 120 degrees up to 200, and when we've compared these results to the hexagonal models, which I'll show the results of on the next slide, what you can observe from the form of the stress on this slide is that it follows a similar pattern to that which was observed in the hexagonal model, whereby the peak stress occurs in line with the adjacent conductors. So this slide shows a comparison between the peak stress values which were observed in the hexagonal models and the half slot model that I've just been discussing. What you can see from this is that the results which were obtained for the half slot model are quite close to the free to move case. In this instance, the difference is of the order of about 15% between the simplified hexagonal model and the full slot. Based on this knowledge, it's possible for us to use the hexagonal model in place of the full slot model to model conductors in the centre of the slot bundle. This allows the area of interest to be considered at a much higher resolution and or with quicker solving times, which is a useful finding. So finally now I'd like to move on to the discussion about thermal cycling and how we can model that. So to start and give you a bit of context for this work, it's worth pointing out it builds on some work which was published at ECCE 2019 on accelerated life thermal cycling tests. In this work we had a number of samples. 4 of them were tested at fixed temperatures to provide a reference for thermal aging of the samples. A further 6 were exposed to different thermal cycling test profiles. It was observed in all the cycled profiles, but failure occurred in a shorter time frame than could be attributed to the thermal aging alone, which highlighted the impact of the thermal cycling in this work. Okay, so to give a bit of an overview into the cycling profiles that were used in this work, as I mentioned, there were 6 samples that were thermally cycled. 3 of them had a peak temperature of 250 degrees, and 3 of them had a peak temperature of 240. In each case, there was a sample that was cycled with a 40 degree cycle depth, one with 60 degrees, and one with 80 degrees. In addition to providing the number of cycles to failure in this paper, it also estimated the amount of life lost due to thermal aging. As I mentioned, there were 4 samples that were run at fixed temperatures, which allowed this to be achieved. The percentage damage caused by thermal cycling can therefore be calculated based on this. Using this, it's possible to scale the values to calculate what the estimated number of cycles could have been if thermal cycling wasn't a mechanism which was also acting on the samples. This is particularly helpful when considering things in FE, as the FE model doesn't consider thermal aging as part of its failure mechanism. So first off, we need to estimate the level of coating stress within the conductors during the thermal cycles. So to evaluate this, we produced the model which can be seen here. It's a similar hexagonal model to the one I've discussed previously, the main difference being that the wire diameter and coating thickness have been modified to match the test samples which were used in the experimental work. Again, the spacing was varied between 0.02 millimeters and 0.3 millimeters, which can be equated to a copper fill factor of about 68% down to 31%. Materials which are used in this model are configured based on the manufacturer's data to try and match it as closely as possible. Okay, so this slide shows the simulated coating stresses obtained for a range of different spacing values. You can see that the general form follows that of the previous model. The specific values vary, obviously due to the difference in geometry. The properties used here are the non-linear material stress strain properties from the manufacturer, assuming a 200 degree temperature. So based on the stress values from the previous slide, combined with the known temperature excursions of each sample, it's possible to determine what the equivalent stress for each of the test samples is. This equivalent stress can then be plotted on the graph shown to the right alongside the experimental scaled cycles values. The expected form of this data nominally should follow the form of a to the xb, which on the log-log scale of that plot should appear as a straight line. The fitted values have been calculated and are shown on that slide as well. Of particular interest is the 0.02 and 0.05 millimeter space data. This is particularly interesting because at a value of 1 cycle, you would expect that the curve should be equal to the ultimate tensile strength value of the material, which in this instance was 66.4 megapascals. While neither of these two curves exactly hit that value, they are both relatively close, and it's a reasonable approximation. It's possible to take the lifetime data predicted in the previous slide and input it into ANSYS to allow different cycling conditions to have their lifetimes predicted. By way of example here, we've recreated one of the samples from the test subject. You can see, shown from left to right, we can calculate the peak stress due to its temperature. We can then also calculate its equivalent stress, which is due to the temperature excursion. And finally, we can use that value to determine the predicted lifetime. You can see here the minimum predicted lifetime is 58.3 cycles. The sample which we were comparing it to experimentally lasted for 56 cycles, which you can see is quite a good correlation between the two results. So to conclude this presentation, firstly, we've demonstrated the use of FPGs for measuring temperatures. We've shown that isolation from external strain is required and demonstrated that a peak tube is a suitable material for this purpose. We've also shown that FE modelling of conductor stress gives a reasonable indication of the likely stress within the winding coating layers. And finally, we've also shown that this work can be combined with experimental lifetime work to predict machine lifetime or damage caused by thermal cycling within electric machines. Thank you for listening to this presentation. I hope you found it interesting.